So chapter 13 is where we start doing what we call vector calculus, which would be the bulk of this course. So what we're going to do first is we're going to review some terminology, some things about vectors, and I know you guys have all seen this before, so it should be review. Normally when we talk about vectors in the textbook, we're going to use bolded letters to indicate a vector, but you can also see vectors with an arrow over it. Vectors are defined by an initial point that we call a tail and a terminal point that we call the head. So if we look at this first diagram, our point P is our tail where we start, and then our point Q would be our head. So we can label the vector as starting, which would be the tail, to ending, which would be our head, and we use the arrow above to indicate the direction it's going in. So vectors have a magnitude, which is just its length, and it has a direction. Vectors are equal if they have the same magnitude and the same direction. Sometimes we call the magnitude the norm of a vector. And we indicate magnitude with absolute value bars. In this second diagram, we can see two vectors. We have a vector u and we have a vector v. And these vectors are equal because they're going in the same direction and they have the same magnitude. Now when we talk about a scalar, we just mean a real number. So scalars have magnitude, but they do not have direction. So the exception to our vectors would be the zero vector, which would be the zero with the arrow over it. The zero vector has a zero magnitude and it has no direction. We're going to do some examples with scalar multiples of vectors. So the scalar multiple of a vector is denoted by c times our vector v. If our c is positive, then the vectors c times v and v have the same direction. If c is negative, then c, v, and v are going to point in opposite directions. So we say vectors are parallel if they are scalar multiples of each other, which means that the zero vector is going to be parallel to all vectors because the zero vector is a scalar multiple. The scalar would be 0 times any vector. Example 1, we want to write the vectors PQ, QR, RQ, and RS in terms of our vectors u and v. When I look at the vector PQ, I'm starting at P, that's my tail, and my head is Q. So I can see that PQ is going in the same direction as U, and it also has the same magnitude. So I can write PQ equal to the vector U. Okay, so remember, vectors are equal if they have the same direction and the same magnitude. Now let's look at QR. So we're starting at Q, that's our tail, and our head would be R. I notice that QR is going in the same direction as V, but it's twice the length of V, so I would write QR as 2 times V. But if I were to write RQ, that would mean that I would be going in a different direction. I would be starting at R, and then I would be going in the opposite direction. So opposite direction just means we have to change that scalar to a negative. This is simply -2 times the vector v. The last vector, rs, tail at r, head at s, it's going in the opposite direction of u, so I know it's going to be -u, and then it's 3 times the length of u. So that would be -3 times the vector u. So the next we're going to talk about is vector addition and vector subtraction. So the first rule we're going to look at is what we call the triangle rule. So that would be a way that we would be adding vectors. So if you have a vector v and a vector u, and you wanted to add u plus v, well, if we start with u, then we're going to look at the tail of u to the head of u. And then when we add our vector v, it's going to be tail of v, head of v. And the resulting vector, u plus v, would have the same tail as u and the same head as v. Another way to look at vector addition is by using the parallelogram rule. So what I'm going to do is I'm going to go back up to the previous example. And if I were to take my vector u and my vector v and shift them, so I'm going to move my vector v over, and I'm going to move my vector u up, then the parallelogram that's formed, you could see that u plus v would just be the diagonal of the parallelogram. And that would be this diagram here. So if u and v have the same tail, and we want to add them, geometrically what we could do is we could just go ahead and draw a parallelogram where u would be the sides of the parallelogram, v would be the sides, and then the resulting vector would be the diagonal to that parallelogram. And that's something that we use quite a bit in application problems, that parallelogram property when we're adding vectors. But we also have vector subtraction. If I take u minus v, I can also look at this as u plus a negative v. So if I have my vector v, I can look at its negative, which would mean the same vector, same magnitude, is just going in a different direction. And now if I look at our vector u plus our vector negative v, I can see that by the parallelogram rule, adding those two would give me this resulting vector u minus v, where the resulting vector shares the same tail. Okay. And its head would be the tip when we draw out our parallelogram. So really what you're doing when you do vector subtraction is you have your starting vector, in this case ours is u, and we're going to subtract our vector v. So the resulting vector u minus v is going to go tail to head of v. So where v ends, u minus v starts. And then the vector u minus v is going to share a common head with u. Example 2, what we're going to do is we're going to write the vector qr as a sum of scalar multiples of w and v. So qr has a tail at q and a head at r. So I could see that by vector addition, I can go tail to head, tail to head. And then I can describe my vector QR as the vector V, right? That would be this piece here, plus, now this is not quite W, it looks like it's 2 times W. So plus 2 times W. Another thing we want to talk about when we talk about vectors is we want to talk about them in terms of their components or their position. So when we look at vector components, what we're going to be doing is we're going to be putting vectors into a coordinate system. So the usual coordinate system would be our XY plane or the Cartesian plane. Now vectored in standard position, which is what we usually use when we're doing application problems, or we can call it a position vector, would be a vector where the tail is at the origin. So that would be this first diagram. Notice that this vector V has a tail at the origin, and it has its head at some point. Okay, so this point in this particular diagram, is going to be the point V sub 1, V sub 2, where V sub 1 is just the length on the x-axis and V sub 2 is the length on the y-axis. So if we were going to describe this vector, we could use vector brackets. So when you are, keep doing that. So when you are describing a vector, just make sure that you're using vector brackets and you're not using parentheses. So I could call this vector V with vector brackets V sub 1, comma V sub 2. And all I need to do to describe this vector, since it's in standard position or it's a position vector, is I just need its head coordinates. Okay? So this would be my vector V. So components would be the V sub 1, V sub 2. They're just our scalars or real numbers. And they correspond to our x and y coordinates. So if we have, and this is position vectors only, if we have 2 position vectors and they're equal, what that means is their components have to be equal. However, and this would be our second diagram, when we talk about equal vectors in general, if vectors are equal, they would have to be equal to the same position vector. So if we look at this position vector in the second diagram, this vector V, it is equal to all these other vectors that have the same magnitude and they have the same length. So now what we're going to do is we're going to compute the magnitude of vectors, since we now can describe them in terms of their components. But since we're talking about vectors in a coordinate system, where we can talk about their components as x and y values, or V sub 1, V sub 2's, then when we look at the magnitude or the distance from the tail to the head, they're going to correspond to points. So the magnitude, again, that's going to be denoted by absolute values, is simply the distance formula between 2 points in the coordinate system. Now when we do compute vectors, we always figure out the components by head minus tail, head minus tail. If you have a position vector, that means its tail is at the origin, so its magnitude is simply the square of the components, add them up, and then take the square root. Example 3, we have the points P and Q, and the point 0, 0, which we'll call O for origin. We want to find the components and magnitude of PQ. So finding the components just means that we're going to do head minus tail. So since it's P2Q, Q is the head, P is the tail. So it's Q minus P. That would be -2 minus 1, comma 7 minus a -3, so +3. In component form, this would be -3, comma +10. So what we've done is we've taken our vector and we've written it in position form. So now to find its magnitude, I simply have to take the square root of -3 squared plus 10 squared, which would be 9 plus 100, or the square root of 109. Notice that to find the magnitude, I didn't have to write this in component form. I could have also just plugged in these values underneath the square root, which would have been -2 minus 1 squared plus 7 plus 3 squared. So I could have just used the distance formula straight away, and I would have gotten the same thing, 109. So we found the components and magnitude of PQ. Now let's go ahead and find the components and magnitude of OQ. Well, OQ is Q minus O, which would be -2 minus 0, or -2. 7 minus 0, which is 7. So the magnitude of OQ will be the square root of -2 squared plus 7 squared, which is 4 plus 49, or the square root of 53. Let's look at operations with our vectors. So let's suppose we have some scalar c, which is again just a real number, and we have our vector u as u sub 1, u sub 2, v is v sub 1, v sub 2. Then when we add vectors, we're just adding component-wise. So u sub 1 plus v sub 1, u sub 2 plus v sub 2. And that would be the same if we're subtracting. It would be u sub 1 minus v sub 1, u sub 2 minus v sub 2. When we take a scalar or a real number times our vector, we distribute that real number to both components of the vector. So let's try using some of those properties in example 4a. We want to evaluate and find the magnitude of 3 times our vector u minus 2 times our vector v. So this is going to be 3 times the vector u, which is 2 comma -5, minus 2 times our vector v, which would be 3 comma 8. Well, I'm going to go ahead and distribute the 3 and get 6, the vector 6, -15, minus, distribute the 2, or you could distribute the -2 and do this as addition. So distributing the 2, I get 6, comma 16. And then I'm going to go ahead and subtract these vectors to get the vector 0, comma -31, which means the magnitude is 0 squared plus -31 squared, which I'm not even going to figure out because I can see that this would just simplify to 31. So we've used just about all those properties up there just for this example 4A. 4B is asking us to find two vectors of length 4 that are parallel to our vector v. So we're going to look at an easier way to figure something like this out, but first I'm going to do it the long way. To find two vectors of length 4 that are parallel to v, well, first of all, what I want to do is figure out the magnitude of my vector v, which is the vector 3, 8. And the magnitude would be the square root of 9 plus 64, which is the square root of 73. So my vector v has a magnitude or a length of square root of 73. So what I want is I want a vector of length 4. So if I take the length square root of 73 and I multiply it by 4 divided by the square root of 73, what I have is 4. So that means if I take my vector and I multiply it by 4 over the square root of 73, the resulting vector will be a vector of length 4 that is parallel to my vector. So that would be the vector, if I were to multiply it out, 12 over the square root of 73, 32 over the square root of 73. So this vector is going to be parallel to my vector, and it's going to have length 4. But I needed two vectors. So remember, vectors are parallel if they're going in the same direction or opposite direction. They're just scalar multiples. So another vector would be the negative of 4 over the square root of 73 times my vector 3, 8. Which I could leave it like that, or I could multiply it through and write it as negative 12 over the square root of 73, negative 32 over the square root of 73. It doesn't matter. They both say the same thing. And in fact, if I wanted to, I could just write this as plus or minus 4 over the square root of 73 times 3, 8. Now you can go ahead and figure out the magnitude of these two vectors, and you'll see that they do have length 4. Another concept that comes up with vectors is unit vectors. So a unit vector is just any vector that has length or magnitude of 1. Important vectors that we talk about all the time have to do with the vectors I and j, which are called our coordinate vectors. They're coordinate vectors because I is the vector 1, 0, and that would be in this diagram. And then j is the vector 0, 1. So I corresponds to the x-axis and j corresponds to the y-axis. The importance of these unit vectors is that any vector v can be written as an ij vector. Now, if we have two vectors written in terms of I and j, they're equal if and only if their scalars are equal. So if we have the vector ai, bj, ci, dj, then a is equal to c and b is equal to d. So the magnitude of this vector is simply the square root of a squared plus b squared. We're going to verify that we can write a vector in terms of the unit vector ij in example 5. So I'm going to start out with the vector negative 3, 10. And I'm going to use vector addition to break this vector up into -3, 0, plus the vector 0, 10. And then in the first vector, I'm going to bring out the -3 scalar and multiply that by the vector 1, 0. Second vector, I'm going to bring out the 10 and multiply by the vector 0, 1. So the vector 1, 0 is simply our I vector, and the vector 0, 1 is simply our j vector. So we've just verified that given this particular vector, we can write it in terms of the unit vectors I and j. And that will be true for any vector. So here are some properties with unit vectors. If we have some positive scalar and a non-zero vector v, if we take that vector and we divide it by its magnitude, we'll get a unit vector, and it's going to go in the same direction as our vector v. If we take the negative of the vector divided by its magnitude, we get a unit vector in the opposite direction. So in general, if you take plus or minus any scalar times v divided by the magnitude of v, you'll get a vector of length c parallel to v. So what we're going to do is we're going to go back to our example 4b, and we're going to look at this vector 3, 8. Remember, the question was to find two vectors of length 4 parallel to the vector 3, 8. So all we have to do is go plus minus the length we want is our c value 4. We're going to multiply it by our vector 3, 8, and then divide by the magnitude of our vector, which we had figured out as the square root of 73. And we're done. We didn't have to do all the math we did before. Right? So we get the same vector that we had before. So what we're going to talk about next is just a summary of all the properties with vectors, and they're similar to the properties that we have for real numbers. So in property 1, we have a commutative property of addition. So commutative just means order doesn't matter. So you can add vectors in either order and you get the same vector. We also have the associative property of addition, which says that if you are adding 3 vectors, it doesn't matter the order that you add. You can add the first 2 first, or the last 2, or any order, and the result will be equal. We have additive identity, which means if you take any vector and you add it to the 0 vector, it remains unchanged. It keeps its identity. And then we have the additive inverse. My goodness. If you take a vector and you add it to its negative, then you get the 0 vector. So there are 2 distributive properties with vectors. The first distributive property is just distributing a scalar. So you can distribute a scalar or a real number across the addition of vectors, and it's the same. But you can also distribute a vector over the addition of scalars, and it's the same. We have multiplication by a 0 scalar, which is simply if you take any vector and you multiply it by the number 0, you get the 0 vector. But we also have multiplication by the 0 vector, which means if you take any scalar times the 0 vector, it's still the 0 vector. It remains unchanged. The multiplicative identity, it's just the scalar 1 times any vector. Vector stays the same. And the last property is the associative property of scalar multiplication. meaning if you're multiplying scalars to a vector, the order that you multiply does not matter. You can either multiply the vector by one scalar and then the other, or you can multiply the scalars together first and then multiply that by the vector. So these are just common properties with vectors, and they correspond to properties that we've had with the real numbers as well. One of the most useful things we have with vectors is writing them using trigonometry. So first of all, our vector is going to be in standard position, and it has to be in standard position because we're going to describe it in terms of our angle theta. But theta is the angle formed by our vector and the positive x-axis. So we're going in the usual counterclockwise direction. So our vector with components AB can also be written in terms of ij vectors, would be the magnitude of the vector times cosine of theta I plus the magnitude of the vector sine theta j. Or using the vector brackets, we can write it as magnitude cosine theta, magnitude sine theta. And here our A value is going to be the magnitude of cosine theta, B is the magnitude of sine theta. A common application of vectors is talking about force. So force is a vector. A property that does come up once in a while is this idea of an object in balance or equilibrium. So if you have an object and you add up all the forces acting upon the object, if it's equal to 0, then that object is balanced or in equilibrium, meaning it's not in motion. Okay. Another common application with force is this idea of work. Example 6 says, suppose a cart is pulled with a force of 30 pounds at an angle of theta equal to 20 degrees to the horizontal. Find the force vector. So typically we just use a capital F, and this is a vector. I have an angle, so that tells me that I'm going to use the description with trigonometry. So my force vector is going to be magnitude of the force vector times cosine theta. So magnitude of the force vector is given here with the 30 pounds. This would be the magnitude of my force vector. So I have the magnitude and I have my angle theta. I'm pretty much done. So I'm just going to draw just a cute little quick diagram of this cart that's getting pulled along. So what I'm going to do is drop this into our coordinate system, where this would be the angle that it's pulled, and that would be the diagram that represents this problem. So my force vector is simply, I'm going to use the vector brackets, magnitude of 30 times cosine of the angle theta, which is 20, comma magnitude of 30 times sine of 20 degrees. And now I really don't know what cosine of 20 degrees is. 20 degrees is really not anything that I recognize on the unit circle. So this is where I would stop. And remember, you can also write this in the ij form as cosine of 20 degrees I plus 30 sine of 20 degrees j. I did want to point out that you either choose vector brackets or you choose ij, but you don't use both. Okay? So at this point I would stop, unless I was going to approximate this vector using a calculator. If I were, don't forget that you're doing cosine of 20 degrees, so make sure that your calculator, the mode is in degrees, not radians. And when I did it, I got roughly 28. I'll use the I since that's the last way I wrote it. I got about 28I plus 10J. Let's look at another common application we have with vectors, and this will be our last problem in this section. Oftentimes we'll use vectors to describe velocity. When we talk about velocity, we talk about speed and direction. Which makes it perfect for vectors because vectors have direction and vectors have magnitude. So here speed in these application problems is equal to the magnitude. And I know this is all review for you guys, but it might have been a while since you've seen this. In example 7, we're going to suppose the current in a river moves southwest at 5 miles per hour. We have a motorboat that's traveling east at 16 miles per hour relative to the shore. Find the speed of the boat and its heading relative to the water. So I think what I'm going to do is I'm going to go ahead and draw myself a diagram. Because I'm given these directions, I'm going to use my coordinate system, and instead of labeling my axis X and Y, I'm going to use north, south, east, and west. So we have the current in a river that's moving southwest at 5 miles per hour. So when we talk about southwest, southeast, northwest, northeast, that means the halfway point between south and west. So I'm going to draw a vector that represents the current. And I'm going to put that vector at the origin. And I'm going to call that vector C for current. Typically in physics we stick to like a U and a V and a W, but I'm going to use C. And I'm going to call that my current vector. Remember, it doesn't matter where I put these vectors, so I might as well put these vectors into my diagram with tail at origin. Because remember, vectors are equal just if they have the same magnitude and they have the same direction. Position doesn't matter, so to make all the computations easy, I'm just going to put tails at origin. So I need to describe this vector. Well, I know that it's going 5 miles per hour, and I know its speed is its magnitude. So I have the magnitude of this current vector is 5, and I'm going to leave off the units. I'm going to use the trig components to describe this vector because I do have an angle. Now remember, we're starting at the positive x-axis, so my angle theta is actually going to be 225 degrees. Now you could just use this 45-degree reference angle, but remember we're in quadrant 3, so cosine would be negative and sine would be negative. So to be safe, I just do from the positive x-axis to my vector, and I'll keep it at 225. So now my vector that represents the current would be 5 cosine of theta, which would be 225, and I'll write it in terms of ij. 5 sine of theta, which is 225 degrees. Now remember, your mode is degrees. So cosine of 225 degrees is going to be negative square root 2 over 2. So this vector is simply negative, sorry, I forgot to write that, negative 5 square root of 2 over 2 I minus 5 square root of 2 over 2 j. And I'm not going to approximate it. I'm going to leave them as exact. Let me go back to the problem. So we have this motorboat. And this motorboat is traveling east at 16 miles per hour. So let me draw another vector that represents the boat. It's going east. I'm going to make this vector longer than my current vector because the magnitude is larger. And I need to name this. I'm going to use B for boat. So something important that I need to be aware of is this motorboat is traveling 16 miles per hour, but it's traveling relative to the shore. So when we say relative to the shore, it means we're standing on the shore and we're observing the motion of the boat. So that would be the speed of the boat plus the speed of the current. So since it's relative to the shore, I'm going to put a little subscript s for relative to the shore. So that's something that we commonly see in physics. So this boat relative to shore will have a magnitude of 16 miles per hour, and angle theta here is 0 degrees. So if I were going to write my vector of the boat relative to the shore, it's just going to be 16 cosine of 0 degrees I plus 16 sine of 0 degrees j. Cosine of 0 is 1, so this is just 16i. And then sine of 0 degrees is 0, so I don't have a j component. So I'm just going to leave this as 16i. But if you want, you could put 0 times j. And remember, you can always write this with our vector brackets. You can always write this as 16 comma 0. That's fine too. It doesn't really matter. We all get the same thing. All right, so I'm going to go back to the problem. I have my vectors represented in my diagram. So this would be my vector that I'm going to call B sub s. So I need to find the speed of the boat, and it's heading relative to the water. Okay, and when we're talking about the water, we're talking about the current. Relative to the water means that this is going to be the speed of the boat without the current affecting it. Okay, so what I'm going to do here is I'm going to draw a vector that is going to represent the boat without the current affecting it. Because the current is going southwest. If this black vector is representing the boat relative to the water or current, that means it's a boat without the current affecting it. So if the current is affecting this boat, what it's going to do here is it's going to push it down, and it's going to actually slow it down because of the direction that the current's going in. Okay? And then the resultant vector would be the green vector that represents the boat relative to the shore. So I need to figure out what that means. Well, the boat relative to the shore, B sub s, that would be using vector addition, where that would be equal to the boat relative to the water, or the current, plus the current, right? Because by vector addition, we're going to have this parallelogram. Or in other words, if I was going to find the boat relative to the current or the water, that would be equal to the boat relative to the shore minus the current, which would give me 16, 0 minus, and my other vector was, I'll write it in component form. Too much writing with IJs. Negative 5 square root of 2 over 2, comma, negative 5 square root of 2 over 2. Remember, these are the same as IJ. It doesn't matter to me which one you use. When I complete my vector subtraction, it looks like what I'm going to get is 16 plus 5 square root of 2 over 2. That would be my first component. And then the negative is a positive 5 square root of 2 over 2. So this is the vector that represents the boat relative to the water or to the current. To find its speed, C, I would simply take the square root of 16 plus 5 square root of 2 over 2 quantity squared plus 5 square root of 2 over 2 quantity squared. After we plug that in our calculator, I get about 19.85, which means the speed is about, I'll go 20 miles per hour. All right, so we still haven't finished answering the question. We found the speed, but remember, we're supposed to find its heading. So when we talk about heading, heading is always a north or south, and then we say how many degrees we go either east or west. First of all, I have to figure out what this angle theta is. So what I'm going to do is I'm going to go back to trig. Now, I can find theta if I notice that I'm going to draw myself a right triangle here. Remember, my vector component wise was 16 plus 5 square root of 2 over 2. That would be like my x value. And then my y value, I could see that as 5 square root of 2 over 2. So what we have here is we have a side opposite and a side adjacent with respect to this right triangle, which tells me that I'm going to be using tangent of theta. Okay? The side opposite, that would be the y value of my vector, which would be 5 square root of 2 over 2, over adjacent, that would be the 16 plus 5 square root of 2 over 2. So these are just the components, x and y, from my vector. So tangent of theta, opposite over adjacent. So I need to write theta equal to tangent inverse of 5 square root of 2 over 2 all over 16 plus 5 square root of 2 over 2. Notice that mathematically we usually keep things exact, but in your physics classes you might have rounded this a long time ago when you're writing your vector in component form. Putting this in my calculator to get an approximation, I get about 10.26 degrees. I'm just going to round this to 10 degrees. So if I were to describe a heading going back to our diagram, it says that I'm going to, here's the tricky part. Since my vector is in quadrant 1, I always start with either north or south. So it makes sense to talk about going north. So we're going to go north. And then we're going to go some theta to the east. Now, since the theta that I found was approximately 10, that tells me that this angle theta that I'm looking at is going to be, out of 90 degrees, that would be about 80. So we're going to go north 80 degrees east. That would be our heading. So always north or south first, then the degree that you're going in direction would be east or west. And in this case, it would be east. So that's it for 13.1. And these sections for the remaining chapters 13 and 14, the sections are kind of long. So I apologize that the lectures are so long. Hopefully you can review the notes first before looking at the video and just fast forward to the part you need to look at. Anyway, that's it for this section.